The A320 is a short to medium-range transport jet. The A320 family of aircraft consists of the A319, A320, and the A321. Minor differences exist between the series. The A320 is a short to medium-range transport jet. The A320 family of aircraft consists of the A319, A320, and the A321. Minor differences exist between the series. The aircraft requires a flight crew of 2 pilots. The required in-flight staff is determined by your airline and is shown on this frame. This frame shows the series of aircraft in the cabin configuration in your fleet. Actual layout of the cabin and operation of the doors will be described in other modules. Notice the location of the service equipment when the aircraft is at the gate. Now here we show some operating limitations of the aircraft. Notice the maximum flight altitude and the takeoff and landing weight limits. Always refer to your FCOM for up-to-date, detailed information. For the remainder of this module, we'll provide an overview of the aircraft features. The AC external power receptacle is located as shown. It is equipped with a flight interphone jack that allows the ground crew to communicate with the pilots during pushback or tow. On this frame, we show the electrical system diagram as it appears when powered by external power. Notice the other available sources of AC power are the engine-driven generators and the APU generator. PDOT probes, static ports, and angle of airflow sensors are installed. A total air temperature probe is installed as well. These items provide air data and angle of attack information to the ADARU. Separate alternate static ports provide static pressure to the standby airspeed indicator and altimeter. The ADARUs provide air data and inertial reference data to the aircraft systems. Much of this information is constantly displayed on the flight instruments. The weather radar antenna is located behind the radome in the nose section of the aircraft. The antenna is a flat dish type, typical for a color radar display. This frame shows the location of various antennae on the aircraft. Control of the landing gear is provided by the landing gear lever. The landing gear normally retract and extend hydraulically, but can also extend by free fall. When the landing gear are retracted, they are completely enclosed by doors. Nose wheel steering is hydraulically operated and can be controlled by the steering hand wheel or the rudder pedals. The steering hand wheel provides a maximum steering angle of 75 degrees, while the rudder pedal steering provides a maximum steering angle of 6 degrees. Each of the main landing gear has 2 wheels. The main gear wheels have hydraulically operated brakes with anti-skid protection. Also, an auto brake system is installed and is used both for rejected takeoff and landing. Flight crew oxygen is provided by a gaseous bottle. The oxygen blowout disc is located as shown. If this disc is missing, the crew oxygen bottle requires servicing before flight. Cabin oxygen is provided by oxygen-generating canisters. Additionally, the cabin is equipped with portable oxygen bottles, or POBs. The aircraft is equipped with a pressurized forward, aft, and bulk cargo compartment. The forward and aft cargo doors are normally operated with hydraulic pressure. The cargo compartments are not ventilated and will not normally support a fire. However, the compartments have smoke detection and fire extinguishing systems. 2 air conditioning packs are installed to provide environmental control. On the ground, the packs can receive compressed air from a ground source, the APU, or the engines. During flight operations, the pneumatic air is normally supplied by the engines. The engine operates at Stage 3 noise levels, allowing the aircraft to meet or exceed the noise requirements that were set for the year 2000. The autothrust system is normally used to set the power in flight. Autothrust is normally engaged after takeoff by moving the thrust levers back to climb power. With autothrust active, the autothrust levers do not move, but the thrust is automatically set according to the phase of flight. At any time, the pilot can manually move the thrust levers to control the power setting manually. The engine is equipped with a thrust reverse system, which is hydraulically operated. The fan airflow provides reverse thrust, and the primary thrust continues to flow normally. Now note, the A320 does not perform powerbacks. The engine fire detection system detects fire conditions. Engine fire protection is controlled from the flight deck and is provided by 2 agent bottles for each engine. Wing anti-ice is applied to the 3 outboard slats of each wing. Wing anti-ice is operated in flight when required by icing conditions, but can also be operated for 30 seconds on the ground for testing purposes. Engine anti-ice is applied to the engine cowl. Engine anti-ice may be operated on the ground or in flight when required by icing conditions. Electrical anti-ice is applied to some of the flight deck windows. Electrical anti-ice is operated for all flight operations to inhibit ice buildup. Electrical anti-ice is applied to the air sensing probes. Electrical anti-ice is operated for all flight operations to inhibit ice buildup. The standard fuel system consists of 3 fuel tanks with fuel capacities shown on this frame. Fuel pressure is normally delivered to the engines and APU by the use of electrically powered boost pumps. Each wing tank directly feeds its own engine. However, either wing tank can feed any engine or the APU by opening the fuel crossfeed valve. The center tank can feed both engines and the APU. However, the APU is normally supplied fuel from the left wing tank. Pressurized refueling is accomplished at the right wing. Note the location of the fueling manifold and the refueling panel. The aircraft is equipped with 3 hydraulic systems. They are green, blue, and yellow systems. The green and yellow hydraulic systems are normally pressurized by an engine-driven pump. The Power Transfer Unit, or PTU, can provide pressure from the green system to the yellow system or vice versa when necessary. The yellow system also has an electric motor-driven pump which is normally used during ground operations. The blue system is normally pressurized by an electric motor-driven pump, but can also be pressurized by the ram air turbine, or RAT. The blue system can operate an emergency generator to provide electrical power when no other source of AC power is available in flight. All primary flight controls are hydraulically operated. Control is provided by 2 elevator aileron computers, or ELACs, 3 spoiler elevator computers, or SECs, and 2 flight augmentation computers, or FACs. The flight control systems operate under laws which provide different levels of automated protection against overspeed, bank, wing loading, stall, and other adverse conditions. The normal law, alternate law, and direct law operating modes are available and are described in the flight control modules. In general, the flight controls require hydraulic operation and require computer signals. We'll now provide a brief overview of all flight controls. The ailerons and elevator are normally controlled by the ELACs. Movement of these flight controls are a computerized response to a side stick or autopilot request. The rudder is normally controlled by the FACs to provide turn coordination and yaw damping. The direct rudder pedal inputs to the rudder are mechanical and require no computer operation. The secondary flight controls require hydraulic pressure to operate. These controls include the spoilers, high lift devices, and trimmable horizontal stabilizer, or THS. The spoilers are controlled by the SECs, and the SECs also provide a backup control for the elevators. 4 of the spoilers automatically augment the aileron lateral commands. Spoilers 2, 3, and 4 can be extended in flight as speed brakes by use of the speed brake lever. As speed brakes, they'll destroy lift and induce drag to decelerate the aircraft or increase descent rates. Spoilers 1 to 5 operate as ground spoilers and are normally armed for automatic deployment during an RTO or during landing. The ground spoilers aid in deceleration during rejected takeoffs and landings. The ground spoilers can only extend when there is weight on the main gear. The trimmable horizontal stabilizer, or THS, is normally controlled by one of 3 electrical motors, which are signaled by the ELACs or SECs. The actual drive operation to the THS is provided by the green or yellow hydraulic system. If the green and yellow systems are not available, mechanical control of the THS is provided by use of either pitch trim wheel on the pedestal. The slat flap control computers, or SFCCs, provide control for the hydraulically operated slats and flaps. There are 5 slat segments on the leading edge, and the trailing edge has outer and inner flaps. The flap lever on the pedestal has 5 detent positions to control the position of the slats and flaps. This frame displays the normal flap settings for takeoff and landing. The outflow valve provides control over cabin pressurization. Pressurization system operates in either the auto or manual modes. Overpressure relief and negative pressure relief are provided by the safety valves. The APU is located in the tail section of the aircraft and provides electrical power and bleed air. Inlet air for the APU combustion enters through an automatic flap on the lower side of the fuselage. APU exhaust is delivered straight out of the aft end of the aircraft. With an inoperative engine-driven generator, the aircraft can dispatch with the APU as the second source of electrical power. Certain restrictions apply and are noted in the MEL. The APU can provide electrical power to the maximum flight altitude. The APU can operate 2 packs up to 15,000, but operates only 1 pack from 15,000 to 22,500. APU fire protection is provided from 1 agent bottle. Controls for this bottle are provided on the overhead panel and on the external APU control panel. The aircraft is equipped with a high-level autoflight system. Inputs to the autoflight are made through the Flight Control Unit, or FCU, or the Multifunction Control Display Units, or MCDUs. The FCU provides a means to select vertical and lateral modes and speed control. When the FCU is used to control the autoflight, the system is said to be operating in a selected mode. The MCDUs provide a means to control the flight management system to fly an automated route. When an MCDU is used to control the autoflight, the system is said to be operating in a managed mode. As you can imagine, we'll learn much more of the autoflight system in this course. Well, this completes our overview of the A320 systems. You'll receive detailed information on all systems later in this course. For now, let's answer some questions on what you've learned.